Yeah, so I'll be discussing improved math with the inverse theorems, and this is joint work with James. And so maybe just as like a general mark, so there will be some computations on the board. I think the message I want to get across is somehow, if you think about this problem hard enough, it's in some sense a very fancy linear algebra problem. And if you can do your linear algebra well enough, you eventually get a good bound. And that's how I like to think about these things. And maybe the message, like there will be lots of symbols on the board, but somehow if you can turn your problem into a purely linear algebra problem, you're in a good place. And that's sort of what's happening. Okay. So I'll start. Let me define the Gowers norm. I think at this point we've had many, many times. So, okay. So I'm actually just going to work on the cyclic group. So it'll be from Z mod NZ to complex numbers. So then the Gowers norm. So this is the expectation over parallel pipets. Of sort of this multiplicative, you're sort of taking multiplicative derivatives and then averaging over parallel pipets. So in particular, delta h of f is f of x plus h bar. I know people like to have the bar in other directions, but I can never get it right. So the focus of this talk will be entirely on the U4 inverse theorem. So it's the theorem from Green-Tau-Ziegler the year earlier, so this is 2011. So also, because I don't want to define Nilmanifolds, everything will be in terms of brackets. Sorry if you object to this. So let delta be between 0.5 and f be a one-bounded function. F is always from Z mod NZ to C. So if the U4 norm of f is bigger than delta, then there exists G such that, so, well, G of x is going to be this funny bracket cubic thing. So I chose some letters, hopefully, that I'll try to maintain consistency with. So you get these kind of things that look like bracket cubic expressions, and then you might get genuine cubic expressions. Oh wow, I forgot a variable. So mx squared plus nx. So something that looks like a bracket cubic expression. This is the floor function. So you have two properties on G. So first, G is like not arbitrarily complicated. So in particular, the expression D there is bounded above just in terms of delta. And okay, G has nothing to do with f so far. What you have is that the exponential of G correlates with f. So the exponential of x in z mod z of f of x e to the G of x. This is bigger than some absolute function of delta. It's bigger. So you have that this expression is not arbitrarily complicated, and you correlate with it. So this is the statement I'll be operating with for the rest of the talk. So as originally stated, I think in this form, these bounds were said to be Tower type. And so then work of Manners, 2018, vastly improved the state of affairs. So okay, he could take D to be delta to be O1 and the correlation to be bigger than exponential. and James last year. So show that you can take logarithms, sort of you can take log in dimension, and you can kind of take a log in this parameter. So the correlation is bigger than quasi-poly. And in the general case, Manners loses 1 log in correlation, and in the general case, there are 2 authors and 100 extra pages. So the goal of the talk is to be discussing a proof of this statement. So in theory, nothing really talking about is my work. Great. Second thing, much of this talk is ripped off of this paper, which I find much, at least for me, a much more concrete way about thinking of the problem. So it's a great read. Okay. So the rest of the talk will be discussing the proof of this statement. Okay. So the starting point is you have this function f. Well, okay, let's start by just unwinding the definition of the Gowers. So the rest of the talk is something like a sketch of proof. And maybe really why it's a reduction to a linear algebra problem.
Surely the delta under the greater than is too much. In Manners results, part 2. I mean, there's already a dependence on delta.
Thank you. Yeah, sorry.
Sorry for making a noise point.
Yeah, really, I want to discuss why this is really a linear algebra. Okay. Let's start. Okay, so if we have that the U4 norm of f is large, then this is the same statement as saying that the expectation over you take shifts of your function and you look at the multiplicative derivative, delta h of f, the U3 norm of this is bigger than delta to the O1. So this is just by the definition of the Gowers. So the starting point of this discussion is this is where you want to start. So we just apply induction. So what does induction give? So there exists H, which is a subset of Z mod NZ, such that the size of H is bigger than delta to the O1 times N, and such that for all H and H, there exists GH of X, which is, just want to keep variables consistent. So for each H in the set, I get some G of H. And what I have is that the expectation over H of the expectation over N of X of delta H f of X times G of X. This is bigger than delta prime. So what have I done here? I've just taken the statement, applied the inverse theorem, the U3 inverse theorem to delta H of F, and sort of written out the conclusion. Now, how good delta prime is a function of how strong your inverse theorem is. So we have a U3 inverse theorem due to work of Sanders. That's quasi-polynomial in strength. But sort of for the sake of discussion, I'm not going to sort of track this quantity of dependence. That falls out kind of naturally if you think about the proof. Okay. So we have this statement. If you stare at it, what is like the data structure of the proof? The data structure is I have this set of Z mod NZ and I have a bunch of these functions. And I know that like my original function f, if I take its multiplicative derivative, it's correlating with these GHs of the issue is like these GHs at present don't talk to each other. These coefficients, like they're arbitrary, somebody wrote them down, and a priori you don't know anything about them talking to each other. So the goal of the proof is sort of to show that these things talk to each other. And if you can show that, that's sort of more or less the proof of the inverse. That's sort of the thing you're trying to prove. So, okay. So to start, this conclusion is initially somewhat unhelpful because there's this unknown function f. So step one is remove f. Okay. And there's just claim. This is essentially due to Gowers, which says, okay, you can remove f at the cost of sort of studying G along additive tuples. So you have a function f from z mod nz to c such that f is one bounded, and functions gh, which are also from z mod nz to c. And such that what I have that the expectation of h outside, the expectation of delta hf of x times gh of x. This is bigger than delta prime, then the expectation over h1 plus h2 equals h3 plus h4 of, we'll get this wrong if I don't want to, gh1 of x, gh2 of x plus h1 minus 4, gh3 of x plus gh4 of x plus h1 minus h4. This is bigger than the prime to the O1. And this is like finite applications of Cauchy-Schwarz. But at this point, our situation has gotten a lot better. We no longer have this unknown function f. And in theory, all we have to do is sort of, so the unknown function f is gone, and we just have the statement in terms of g's, and we want to figure out what we can say about relating these g's to each other. And sort of almost all the proof just operates with, I think even all of the proof just sort of operates with only this assumption kind of. And you're going to use this to try to learn some structure like gh of x. Okay. So is this starting point clear? Okay. Okay, so maybe before diving in, let's sort of maybe see, I think many more people are familiar with the proof of four-term arithmetic progressions due to Gowers. I'm going to claim that this sort of is like, looks like that. Okay, so this is the U3 case. This proven by Zing and Tao. Various of these steps appear in the proof of four-term arithmetic progression. Okay, so what happens in this case? So this 4 becomes a 3, this 3 becomes a 2, and sort of what we have is that for many h, delta h of f, the U2 norm, this is large. So at this point, you can apply Fourier analysis. And what do you get? You get that there exists theta h in R mod z such that the expectation over h and z mod nz of the expectation of x delta h of f, h of f theta h of x. This is bigger than delta to the O. Please ask questions while I'm erasing, if there are any questions. So now, let's apply this and this lemma. So what does this tell us? So for delta to the O1 times n cubed, many additive couples, we have that the expectation over x of E of theta h1 plus theta h2 minus theta h3 minus theta h4 times x, that this is bigger than delta to the O1. Okay. And this conclusion is, this is summing a geometric series. So you have theta h1 plus theta h2 minus theta h3 minus theta h4. So this is some small numbers. Delta to the O1 over n. But this is a situation that we're happy with in additive combinatorics. This is basically saying that the map h to theta h is linear 1%. And we have powerful tools to handle this. So in particular, okay, you need Bollock summary. So you need Bollock summary Gowers, and results towards the Freiman-Ruger conjecture over the integers, polynomial Freiman-Ruger conjecture over the integers. So uses work of Susask and Sanders. And what you get in this, so you can phrase this in terms of Bohr sets. I'm sort of phrasing everything in terms of brackets. So a morally equivalent, I think actually equivalent statement probably is that you get the theta h is equal to alpha j plus theta j h, where a d prime is, okay, there's some error term here in terms of delta, which I'm not going to write. And you get that the number of phases you need, something like log 1 over delta to the O1. This is more or less just the dimension of the Bohr set. This is writing it this way is sort of in the Green Tau paper. But okay, so maybe these first 3 steps are morally very close to what's in Gowers' proof of 4-term arithmetic progressions. So let's just plug this back into the conclusion. So okay, I didn't write this. So this isn't true for literally every h. This is true for greater than and different shifts h. Okay. And okay, so what does this give? So this gives that the expectation over h in z mod nz of the expectation of delta h of f, this down really.
A minor technical point here. Your cross correlation statement involving only the G's, aren't you going to need this sort of hereditarily for the set of H's? When you substitute back in.
So, okay. So my set of H's, okay, you can sort of define G of H to be 0 outside a set of H's where you have correlation, and then you sort of don't plug back in here. You really, but you plug back in there. Yeah, setting things to 0 is how, at least I always avoid these kind of things. Yeah. This is bigger than. Okay, I'm no longer going to pretend I'm going to try to track quantitative dependencies. I'll comment on that at various points. And okay, so this is morally in Gowers' 4AP paper, and sort of we've already gotten a lot of structure here. We've shown somehow there's like a quadratic here. X and H are degree 1. This is a degree 2 object. So we've already done a substantial amount of work, but this is really not enough to finish. To finish, you need an argument of green and tau. This goes under the name symmetrization. And what you can then prove is somehow alpha and beta are symmetric in the right way. I'm not going to say anything about this. Suffice it to say, if you look at this argument, at least in the U3 case, it's the only inputs are finite applications of the Cauchy-Schwarz inequality and equidistribution for expressions that look kind of like this. So if you believe that equidistribution is efficient and Cauchy-Schwarz, so let's just pretend we're trying to get some finite number of logs for now. So equidistribution is efficient, and symmetrization, like the other part of symmetrization, is just the Cauchy-Schwarz inequality. So then very clever applications of the Cauchy-Schwarz inequality, just Cauchy-Schwarz, so it's kind of by fiat efficient. So in some sense, I'm not going to worry about this step. I'm only going to worry about this step where at least we start seeing some. So okay, so in the U3 case, some degree 2 object. In the U3 case, some degree 3 object. And that's all I'm going to discuss. So I'm going to erase a bunch now. We're now just going to try to run this argument for the U4 case. We'll get stuck at some point, and we'll discuss what happens when you get stuck. Okay, so I wrote some slightly ugly expression there. For the rest of the talk, Ci of H and Di of H are equal to 0. It's fine. Okay. So what do we have? We have that for delta to the O1 n cubed additive tuples of H1 plus H2 equals H3 plus H4 that the expectation over x of e of, sorry, the expressions get long and so I'm now trying to solve this like invert. I'm trying to sort of understand what possible solutions are there to this this kind of really weird, almost a functional equation. Like I get some really weird coefficients flying around, and I know that for many additive couples that this is large. And my job is just to classify this.
Sorry, just a small question. So f will no longer appear in everything that follows. Everything that we knew about f is encapsulated in the statement about g.
So it's encapsulated in this statement, and remembering that you had this inductively.
Oh, okay, okay. Inductively over what? That's what I haven't understood yet. What's induction? Which variable does induction work on?
Sorry, I'm not inducting. I should be more precise. So I sort of have, okay. So you remember the statement that you have this from somewhere, and you have a set of additive couples.
Yes.
At various points, I might refine the additive couples. This delta to the O1 might become some like smaller constant in terms of n. And so then eventually what I'll try to do is derive a statement which holds for 1% of the h's.
Yes.
And I can set it up so that like I can sort of set gh of 0, g of h of x to be equal to 0 when h is not. Suppose this was true for every h. Then like any conclusion I derive on some positive fraction of the h's, I can sort of plug that back into the statement. What you do is you sort of set gh of x to equal 0 when you don't correlate with this derivative. And so then you derive that gh of x has some structure on some positive fraction. And so then you get for a positive fraction of the derivatives that you correlate.
You're going to iterate this claim or not?
I derive conclusions from this claim. I derive some structure on this, and then I plug back into here. And then I run the rest of the argument.
And you're going to do that several times, and that's why it's called an induction, or you're going
So
to.
the induction is the induction is on the parameter US. Like I'm proving the U4 inverse theorem, I applied the U3 inverse theorem. That's what I mean by induction.
Oh, okay.
Sorry, I didn't mean anything more deep than that. But apologies.
Thank you.
Okay. So the thing that's kind of scary about this, the first time you look at it, is that okay, there's like this is kind of strange, right? There are a bunch of these like h terms floating around, and there's like h's and x's floating around, and they're dependent in some complicated way. The first thing to do is sort of remove these shift parameters. So very roughly, you sort of so you solve the problem by looking at top order coefficients. Okay. So why is this sufficient? Okay, so this is something like step 2. Okay, this is the way I'm going to explain it here is just it's some bracket algebra. So okay, when you think about this statement, you should think about things like the sort of quality of a term. Okay. So there are a couple things to say here. So very roughly, how you're supposed to think about this proof is something like alpha are secretly h-dependent terms. So terms like this are more complicated than, and these are, so terms with a bracket in it are more complicated than terms without a bracket in it. And these are more complicated than linear terms. And sort of the first step is to realize that if you adopt this philosophy, that these shifts don't matter. This is a computation which I will now show, just for the sake of believability. And this is almost exactly what was in James's talk, but I'll show it just because this is kind of an important thing. Sort of, you only need to track top order information, and this is crucial for. So I care about this term mod 1. So this is the same, so I can apply distributivity on the outside. So notice that this term is now degree 1 in X. So I'm just going to call this jump. It might depend on H in some nasty way, but it's lower degree in terms of X. Okay. Then I sort of try to make the fractional part linear. So I write this as beta X plus beta H plus alpha X times so essentially by the manipulation, so I only care about this expression mod 1. Okay, so I can make a series of simplifications for this. This is an integer, so I can put a fractional part around here. These three arguments add up to each other. So if you do algebra carefully, it's equal to the same thing with with brackets around it. And from James's talk, we sort of saw that things with two brackets around it are either secretly degree 1 objects. Great. So basically, what I can do is I can apply this, and if I'm willing to keep around this massive junk error term, I can sort of simplify this correlation. So what do I get? I get that for delta to the O1 and cubed additive tuples, expectation over X of E of so somehow I sort of removed the shifts from the equation. And it's worth saying this is some kind of like, it's not obvious that this is an okay thing to do. You're sort of giving up information. I mean, there's secretly structure in these terms. And it turns out that the symmetrization argument very roughly is trying to capture some structure in this term. But for the purposes of my discussion, you actually just don't need to really worry about this. So for most of the proof, you can kind of just say, okay, this goes away. This is carried around as an object in the proof, but you can sort of operate modulo these lower order terms. Okay. The thing that's sort of left to do, and I want to do the last like 20 minutes, is sort of convince you at this point that this is actually like a linear algebra problem. And that's maybe the thing I want to sort of. I need to get that off my list. So the question is, how can star possibly happen? Okay, let's try to figure out cases where this can happen. So what do I have? I have these set of coefficients for each h, and I want to say that for many additive tuples, I have this situation. So you can derive a bunch of cases where this happens. So let's consider where d1 equals 1. So what can happen here? Well, what I could do is I could set the d equals 1, so the sum vanishes. Suppose all these b's are the same as each other. So if bi of h, this doesn't depend on h, so it's just equal to b, and alpha I of h, well, this is equal to universal constant alpha times h. So in this case, like this is beta x, this is beta x, this is beta x, this is beta x, and the front three terms cancel. Great. You fudge around, it also works if you flip the parameters. This is beta h. This is not so obvious, but it is true. Okay, so this is one case. The second case is, okay, I don't actually need this to be kind of exactly additive. I can sort of generalize this example. So if bi of h is still equal to beta, I only need this to sort of hold on a dense set of additive tuples, so I can sort of take all the examples coming from sets or less formally, or we can just take beta j of h. So different fractional parts. And this will also hold for 1% of things. This is just saying that alpha is 1%. Okay. So, okay, we sort of see where linearity is coming into the picture and sort of. Okay. Not to write what the third case is, so I will try to figure it out live, but that's maybe a bad idea. Okay, let's try. And case 3 is sort of, you don't come from any linear relations. What instead happens is that you sort of have short linear relations between your coefficients. What is the right way to do this? So I think, yeah, so, okay. The easiest way to see this is take like d1 equals 2, and, okay, so beta IH is arbitrary, and alpha 1h equals minus alpha 2h. So when I sum these two terms, okay, so beta 1h equals beta 2h is arbitrary, and alpha 1h equals minus alpha 2h. That's also arbitrary. So what I've done here is I've written a sum of two things, and I sort of made sure every term like literally is the first term for I equals 1 and the term for I equals 2 are literally next to each other. And so it cancels. And so, yeah, this is so sketchy that maybe claim is the wrong word, but okay. Sort of maybe the arguably key claim in Green-John-Ziegler, this is all that happens. What do I possibly mean by this statement? This you should sort of think of as there's a short linear relation that holds between the coefficients. So notice that, okay, what have I said? I've said b1h equals b2h, and alpha 1h equals minus alpha 2h. So it's some linear relation between the coefficients, which holds for every, for all these, like for each h individually, and it's the same linear relation for all the h's. So somehow there's this expression, I like wrote it with different parameters, but secretly it was a lot simpler. That's one case. The other case is somehow something more familiar from, let's say, the proof of the U3 inverse theorem. It sort of looks like 1% linear functions. And I sort of fix BIH so that it's fixed, and this is what you want to. And one of the parameters is kind of fixed, and then the other one is sort of varying linearly. And that is also a perfectly fine conclusion. And sort of combinations of these two cases are the only things that can happen. Okay. So at this point, you sort of have to, unfortunately, you can't just keep doing brackets. You have to introduce a no manifold somewhere, and okay, it happens here. So it turns out the right way to think about the statement is to write it on a no manifold and then write down the equidistribution theorem. Okay, so I'm just going to work out an example. There's ones on the diagonals. So this is a 2D plus 1-dimensional no manifold. So there are zeros in the middle, r's on the top, r's on the bottom. So this is step 2. The commutator of G with itself is a bunch of zeros except for the top coordinate. I think we've already seen this automorphic function. So okay, so let little g be just some specific element, alpha 1 through alpha d and beta 1 through beta d. Okay. H is 1. So there's a function a priori, it's only defined from G to C, where I take this and I look at the exponential of minus I equals 1 to D of alpha I floor beta I C. But it turns out, okay, so I also need the lattice here. So I need a discrete group inside of this. The discrete group is you just replace every copy of R you saw with a copy of Z. What it turns out is that f of G of gamma equals f of G for gamma and gamma. And okay. And so what is the relationship between things like that and things like this is that f of G of m times gamma, this is a lie, but only barely. So it's the same thing as these bracket polynomials, or these bracket polynomials that we've been looking at. And the point is that the statement for being not equidistributed is a linear algebra statement in these coefficients. So the following is a theorem of Green and Tau, but you can definitely derive this from the work, but writing it like this to the James, for a reason I will say. So let alpha I and beta I mean 1 over n times z with n prime. So if delta is between 0.5 and n is bigger than this single exponential dimension quantity, and we have that this really erase that. So if I have that this, oh, thank God, if this is large, then there exists V inside R to the 2D. Okay, one extra thing, right? Before I finish the statement, I left this helpfully on the board. I need the commutator of G and H. So the commutator has to live inside this subgroup. So I just need to specify this coordinate. It's kind of nice. It's sum of alpha I times beta I prime minus beta I times alpha I. Okay. So there exists V in R to the 2D such that, so okay. I'm also just going to write this as the commutator of, so this is some linear, like bilinear form in the like the non-prime variables and the prime variables. So I'm just going to write this as omega of alpha 1 alpha d beta 1 to beta d alpha 1 prime alpha d prime beta 1 prime beta d. So this V has a special property. What it has is that the commutator of V with itself is equal to 0, and 2 of V is delta to the minus O d to the O1 rational. What does this mean? This means that you can write, so V I've identified as a subset of R to the 2D. You can just write it as an intersection of kernel vectors that are kind of short. So it's V in R to the 2D such that, so Wi comma V is equal to 0, or 1 less than I less than R, and Wi is these are integer vectors, and they're not too long. You can, it's a good exercise maybe to like, so this is a statement. I sort of pulled a rabbit out of a hat here by writing this in this way. I think this is what James means by sort of you have enough relations to sort of simplify the sequence. If you sort of plug in these relations into this and do these various bracket manipulations, what you'll find is that you can sort of simplify this to something that's linear in X. And in some sense, this information is like a complete statement. What I mean by this is, if you're going to run a proof like this, you have this giant junk term floating around, and sort of things that are inside the junk we're not trying to look at. This proof is sort of giving you, the statement gives you all the information you could hope to have about these top-level coefficients. Because once you've learned this information, secretly this expression is now you could rewrite it to be in the junk term. So this statement is complete in some sense. You've learned all you possibly could have. And okay, the rest of the proof is sort of then gluing together these linear spaces. So I'll just say one last thing. Okay, so if you apply theorem to star, so okay, I have this star thing, I can apply this theorem to it. I get that this like long vector alpha h1, sorry, these are the coefficients of h1, the h2 coefficients, the h3 coefficients, the h4 coefficients, and these lie in some subspace V of h1, h4. But you get lucky, sort of, you know that V is a rational space. And sort of you can say, okay, there are not that many rational subspaces. So you can just apply the pigeonhole principle and say, okay, actually, I know that for many additive couples, these four things lie in some fixed rational subspace V. And the output of the theorem is that you want control. You want to say that this tuple lies in some vector space plus, but that can't be exactly true. because you know there are these bracket linear functions. So you need to write a correct statement of this form, but then you sort of try to deduce from here some structure, from this fourfold substructure on the single. And that's sort of, this is a purely linear algebra problem when you state it this way. And the content of the proof is solving this linear algebra problem. I'm not going to say anything else, so that's where I'll end.